Okay, welcome to the third in the series of lectures. So last time I was talking about Frisch. Now, as I told you, Frisch came to England, and when I was a student at Queen Mary College, now Queen Mary University of London, then my professor, Professor Mike Williams, uh, and took me to a conference in central London organized by the Royal Institution of Nuclear Engineering, whose president was Geoffrey Lewis, later my PhD supervisor at Cambridge. So Mike Williams introduced me to Otto Frisch, and I actually shook hands with him and told him what a great honor it was for me to meet the great scientist who had discovered nuclear fission. So I met him, and later, I think a few months after that, Dr. Abdus Salam, physicist at Imperial College, got his Nobel Prize in Physics, and I went to congratulate him, and we became very good friends, and I really learned from him a lot. So let's continue with our thing, the atom. Now, atom, as you saw last time, it's just a little thing in the center of the nucleus is a little dot in the center of the atom. The diameter of the nucleus is about 10 to the minus 15 meters, and the diameter of an atom is about 10 to the minus 10 meter. We call that the angstrom. And so inside the nucleus over here, you've got protons and neutrons. Now, the mass of a proton, the mass of a neutron is 1.67, I think it's 8 times 10 to the minus 27 kg. And this is 1.675. You can check in the books. So it's a little bit less than that of a neutron. The mass of an electron is about 9.31 10 to the minus 31 kilogram. Now, when we come to such small numbers, we talk of mass in terms of energy because there's the conversion E is equal to mc square. And so we talk of mass in terms of so many MeVs. Okay, so basically, if you look, for example, at a carbon atom, now this means that there are uh, uh, six protons. So because the atomic number is 6, so protons is 6. The number of neutrons is 12 minus 6, which is also 6. The number of electrons is 6. So if you multiply these numbers by these numbers, and if you take Avogadro's number, Avogadro told us that there are about 6 times 10 to the 23 atoms per gram atom. Then you will find that so many atoms of carbon would weigh, and we'd call that the atomic weight of carbon. So this would be about 12 grams. So basically, Avogadro's number is such a big number. And so the atom is, if you multiply, then you can actually get the weight of the atom, which is so small. Okay, now you might think that how do protons and neutrons live in the same house when a proton is positively charged and a neutron is neutral? So if it were negative, then we would say that yes, they could live together. Now, are protons and neutrons elementary particles? And Dr. Salam was the man for that. And so I used to ask him a lot about elementary particles. Now, that's not my field, but a neutron is basically made up of more fundamental particles called quarks. And the fact that they live together is due to the binding energy of the nucleus. Now, binding energy means that if you were to take apart all the nucleons, the protons and the neutrons, and calculate their mass, and then calculate the mass of them together, tightly bound in the nucleus, then those two numbers would not be the same. In other words, 3 plus 2 would not be 5. So it would be maybe 4.8. So where does the difference go? Now, the difference goes into energy, which is binding the nucleus together. So, in other words, to separate, to break free the neutron from inside the nucleus, you would need to hit it with energy to smash the nucleus. So that's called the binding energy. Okay, now let's come to Fermi. So basically, Frisch was in 1938 onwards, and of course, then he went to Birmingham, he went to America, he took part in the Manhattan Project. Now, Fermi, another great scientist, truly, physicist, engineer. Now, he's the man who could, with an envelope at the first atomic test site, with an envelope, he just put it in front of the blast wave and said, this is 20 kilotons. So basically, Fermi was a genius. And in 1942, and I don't remember the date, let me see, maybe I've got it written somewhere over here, on the 2nd of December, 1942, in the University of Chicago, he was the head of the team that made the critical pile CP1, the first nuclear reactor in the world with natural uranium, about 5 tons. Check all these numbers in the literature, but about 5 tons of natural uranium and about 330 tons of graphite. So they were able to make it critical. So criticality in nuclear is the key, where you can sustain a chain reaction. Now Fermi went on to develop CP2, and he basically Fermi age, beta rays are all due to him. Finally, in this lecture, let me come to neutron energy. Now, the neutrons which come out of here cannot survive for a very long time. They can survive for about 18 minutes as free neutrons. They have energy. So if I draw a vertical line like this, and you know that energy is related to temperature by the Boltzmann constant. The Boltzmann constant is about 10 to the minus 4 eV per Kelvin. So in this room right now, let's say the temperature is 300 K. So 300 K, if I multiply this number by 300, what do I get? I get 300 times 10 to the minus 4. So it comes to 0.03. So thermal energy is about 0.025 electron volts. That's the energy of the molecules in this room, air molecules. And if you calculate the speed of these molecules, it's about 400 meters per second. So by our standards, they're very fast, but by comparison with we do with the speed of light. So compared with the speed of light, they're very slow. The fastest neutrons are around 1/10 of the speed of light, so they would go in the MeV range. So you can see that these are the neutrons that we call fast neutrons, and these are the neutrons that we call slow neutrons. Since the slow neutrons are in thermal equilibrium with the room, with things in the environment, so we say that thermal neutrons to fast neutrons is the energy spectrum of neutrons. Now, in the next lecture, I'm going to talk a little bit more on neutrons, how they go through matter, and then we'll come to our main topic of talking about the three formulations. Thank you.